Hi everyone, today we'll be looking into Otto Cycle. Okay, so Otto Cycle consists of two constant volume process and two isentropic processes. Okay, so two constant volume process and two isentropic process. Now, first thing is we'll teach you how to draw a PV and a TS diagram for Otto Cycle. So this will be your pressure axis, okay, and this will be your volume axis. So this is going to be a PV diagram, and this will be your TS diagram, temperature in Kelvin and the entropy. Okay, so before we start on drawing the PV and the TS diagram for Otto Cycle, which consists of two constant volume processes and two isentropic processes, so we are now going to basically look at how the curves, okay, the temperature and the entropy curves looks like in PV, and then how the pressure and volume line or the pressure and volume curves looks like in TS diagram, which we have done in previous podcasts. Okay, so this is going to be a PV diagram. So from here you can see these are the entropy curves. Okay, so the higher the line or the curve, the higher will be the entropy. So we can say S4 is greater than S1. Then for the temperature line or the curve, we have T1 to T4. Okay, so the highest temperature is T4 and the lowest temperature is T1 on the PV diagram. So if let's say, for example, we are looking at two isentropic processes, then we have to draw two isentropic curve on the PV diagram, and as well as two constant volume line on the PV diagram. Okay, so then the next thing is the TS diagram. So V4 is less than V1, so volume is inverse. Okay, so the higher the curve, the higher the line, the lower the volume. So you can say V1 is greater than V2, is greater than V3, and is greater than V4. So V4 is the lowest, V1 is the highest. Then when we look into pressure line, it is slightly different. So the higher pressure, the highest pressure is P4 and the lowest pressure is P1. So you can say P4 is greater than P1. So since we are going to look into Otto Cycle, okay, so from the PV diagram, the first thing is, since there's two processes, so I have to draw two constant volume line here. So this is the two constant volume line on your PV diagram. And then on the TS diagram, to draw your volume line, you should draw it as in the term of a curve, in the form of a curve like that, what I've shown you in your TS diagram. So that should be your first one, and that will be your second one. That is for the constant volume process. Then we look into the isentropic. Okay, so on the PV diagram, so the entropy curves looks like that. So from here, okay, on the PV, we're going to draw two constant entropy curves on the PV diagram for isentropic. So that is the first and the second. So on the TS diagram, basically it's easier because this is your entropy axis. So you just need to draw two vertical lines. So 1 and 2. So once you have got the diagrams drawn like that, so what you need to do is each intersection points here, you just need to mark it down. Okay, so you have 4 points here. So you have 1 process, 2 process, 3 process, and the 4th process. The same as for the TS diagram. So you have the 4 points. So each here 2 state points represents one process here. So 1, 2, 3, and 4. So then the next thing is we're going to put in the point 1, 2, 3, and 4, the state point 1, 2, 3, and 4 on both PV and TS. So be careful when once, if let's say for example, you choose to put your point 1 on PV diagram first, then your TS diagram, the point 1 that you're going to place here should be, okay, should be the same as what you have put here for your point 1. So that means it should be tally with the point 1 that you have put in your PV diagram. So this should be your point 1, 2, 3, and 4. And remember, it's in clockwise. So that is why the points I put it in clockwise, okay, formation. So point 1 is actually on your PV diagram is actually at the lowest pressure. So since it's at lowest pressure and this is an isentropic process, so on the TS diagram you choose to see the isentropic should be this line and this line here. Now here point 1 is actually at the lowest pressure, so it should be at the lowest temperature here. So this should be your point 1. Okay, so your point 1, 2, 3, and 4. So you're almost done. So now the next thing is, let us put in the arrows, which is in clockwise direction. Okay, so we start with PV diagram. So this is from state point 1 to 2. And then another arrow from 2 to 3. And then another one from 3 to 4. And then back to state point 1. So it completes a cycle. That is an Otto cycle on the PV diagram. Okay, so and then on the TS diagram, the same thing. Put in the arrow, state point 1 to 2, and then 2 to 3, then 3 to 4, and then 4 back to 1, complete the cycles. Okay, so then we have the Otto cycles done. And remember that, okay, why we are referring to PV and TS diagram. PV actually refers to work done, and then TS actually refers to the heat transfer. Okay, so then from there, okay, since we have known that Otto cycle or constant volume cycle, okay, consists of 2 reversible constant volume process and 2 reversible isentropic, and it is equivalent to a petrol engine cycle or a 4-stroke internal combustion engine cycle. So therefore I have 4 cylinders here which I've drawn, and then the first and the third diagram, okay, it is isentropic, so that means it must be perfectly thermally insulated. Okay, so and then from the diagrams you can see I have put in 2 fixed position here. One is called the bottom dead center or the outer dead center. The next one is the top dead center or the inner dead center. So the piston should slide forward and backward within these 2 fixed points here. So if let's say in terms of distance or length, the length or the distance that the pistons move from BDC to TDC or from TDC to TDC is considered as the distance which we call stroke, S-T-R-O-K-E. So when the pistons move forward from BDC to TDC, that is considered as 1 stroke. Then when it moves from TDC to BDC or ODC, outer dead center, we call it as the return stroke. That means the 2nd stroke. So from this Otto cycle, which is the constant volume cycle, we have isentropic compression when the pistons slide from the outermost position to the innermost position, that is from BDC to TDC. And then at that particular instant, as it is at TDC, that means at its inner position, okay, we just imagine that the piston is being stagnant or stationary at a very short period. And at this moment, the air and fuel mixture within the compartment, within the space here, which we call this as the system, the thermodynamic system, okay, that is the mixture of air and fuel. So what happens is it ignites, and then you have heat supply, and this heat supply is at constant volume process. It's at a constant volume process. Then after that, when it moves from 3 to 4, that means what happened is the gas just now would expand. So when it expands, it tends to pushes the piston outwards. So the pistons will move from TDC back to TDC, okay, which will generate work that we call as work output when the system undergoes an expansion. Okay, that means increase in volume, you have work output. And when the piston is sliding in, okay, while the air is being compressed, we say work is transferred to the system. Here, work is transferred away from the system. So while compressing the air, we say we have work input. So that is a decrease in volume. Then after that, the fourth diagram, the fourth cylinder, as you can see, the pistons remain stationary at the bottom dead center, that means at the outermost position for a very short time. So the volume inside here remains constant. And at this period of time, heat is removed or heat rejected. We have heat rejected, and that will cause a decrease in entropy. Okay, we know that when entropy changes, that means there is a heat transfer. When there's a heat transfer to the system, we call it as heating or heat supply. That causes increase in entropy. When heat is transferred out from the system, okay, crossing the boundary, we say that is heat rejected or that is a cooling process. Now, from this, you can see, okay, how the pistons move from bottom dead center to top dead center and remains at that inner position while the burning of fuel taking place. Then after that, what happens is it expands and pushes the piston outwards. Pushes the pistons outwards, so therefore it produces work. And at the last diagram here, you can see, okay, that this, okay, what happened here is heat is being rejected and cooling is taking place, okay, within the boundary of the system. Okay, so and you can see at based on each of these diagram, I have got the PV diagram starting from move from state point 1 to state point 2 for the first diagram. Second diagram we have, okay, it moved from state point 2 to state point 3. The third diagram, it moves from state point 3 to state point 4. And the fourth diagram, it moves from state point 4 to state point 1. Okay, so now and on the PV diagram now, on the next part, okay, what we are looking at is something which we call volume ratio. That is to define the thermal efficiency of the cycle later. Okay, so now when you look at the PV diagram, or based on the 4 diagrams just now, you got to know that the pistons is moving from BDC to TDC, and then from TDC it stop for a while and then move back to BDC, and then it stop for a while and then move back to TDC. While it's moving to from BDC to TDC or from TDC to BDC, the volume that is displaced, the volume of gas or the volume of air and fuel mixture which are being displaced is called the swept volume. And then the volume which, okay, now in this diagram, okay, it actually comes into contact with the cylinder wall. Okay, but then in actual practice, it would have a clearance in between the piston and the cylinder, and that would give you the clearance volume, which is the minimum volume. The maximum volume would be the swept volume plus the clearance volume, or basically when you look into PV diagram, which this point here is the origin, and when you look at it, V1, if you have V1 or V4 here, which is the same, which is equal, would be the maximum volume, which is equals to the swept volume plus the clearance. While then when you are looking at state point 2 and state point 3, which is also a constant volume process, so from V2, V3 to the origin, that will give you the clearance. So you can say clearance volume is actually the V2 or V3. The maximum volume, which is swept volume plus clearance volume, it is actually the V1 or V4. Okay, so you have the PV diagram for work and the TS diagram for heat. And remember, okay, that from the previous slide or from the previous podcast or content, okay, I did mention that when the entropy increased, you have heat supply. When the entropy decreases, you have heat rejected. When the entropy remains unchanged, then you have no heat transfer. So point 1 to 2 here, as you can see from the TS diagram, remember TS diagram is the area of TS diagram equivalent to heat transfer, okay? So from point 1 to 2 here, okay, constant entropy, that means there will be no heat transfer from 1 to 2 and no heat transfer from state point 3 to 4. So the heat transfer only happens from 2 to 3 and from 4 to 1. So from 2 to 3, since this is an increase in entropy, it is an increase in entropy. So therefore, 2 to 3, state point 2 to 3 here represent heat supply. And 4 to 1 here represents heat rejected. Okay, heat rejected because of decreasing entropy. Okay, towards the origin. 2 to 3 is away from the origin. 4 to 1 is towards the origin. So this is increase in entropy. Here you have decrease in entropy. So therefore you have heat supply, heat rejected here, zero heat transfer and zero heat transfer here because it's isentropic or adiabatic. So here I will have top dead center as TDC, or sometimes it's called inner dead center, which is the innermost position of the piston, which it can reach. Okay, and then BDC is the bottom dead center or the outer dead center. That is the outermost position which the pistons can reach. Okay, so that is this and this. Okay, then it comes to volume ratio. So volume ratio, basically when you look into what ratio, term ratio means it is referring to a numerator and a denominator with the same, okay, how to say, same quantity. Okay, so when you look into ratio, volume ratio basically is defined as the maximum volume over the minimum volume. So our maximum volume just now was V1 or V4, and the minimum volume, that is V2 or V3, or the maximum volume is swept volume plus clearance, and the minimum is clearance. So therefore we can define the term volume ratio, which, okay, is given with a symbol of R with a subscript of V. So that is defined of maximum volume over minimum volume. Later on, you will get to know, okay, what is the use of this term here. Okay, so we just put in our maximum volume, which is equals to swept plus clearance, and minimum volume, which is equals to clearance. So which is V1 over V2 or V4 over V3. Remember, V1 equals to V4 because it's constant volume here. V2 equals to V3, which is also another constant volume here. So swept volume, actually this swept volume here can be found by applying this formula here, which is given as pi d squared over 4 times L, where d represents the diameter of the piston or the bore of the cylinder. L represents the length which the piston travel, the distance which the piston travel forward or backward. That is called a stroke. L is considered as the stroke. Okay, D is the bore of the cylinder or the diameter of the piston. L is the stroke, which is the distance the pistons travel from between the two positions, that is BDC or to the TDC, or from TDC to BDC. Okay, so the next part we are going into thermal efficiency. Now remember, thermal efficiency is defined as the desired output. Network output is our desired output for an engine. For an engine, the desired output is always refers to the network output. That means the work produced by the engine. So the thermal efficiency or efficiency, when we look at the term efficiency in general, is defined as desired output over required input. It also can be referring to human beings. Human beings can be considered as a heat engine as well. So which the work that we do is considered as the work output, and the food that we take or we eat, that is considered energy supply. So the energy supply or the required input here is the heat supply, which we have referred just now. Okay, the heat supply. Okay, afterward I will go back into the heat engine part to show you how we got the net is equal to heat supply minus heat rejected, and so. Okay, so net work is actually equals to heat supply minus heat rejected. Okay, so when you simplify or when you manipulate this, you will get 1 minus heat rejected over heat supply. From the previous diagram, we got to know that heat supply and heat rejected is actually based on constant volume process. So the constant volume process for heat supply is equals to, for heat supply, constant volume process is equal to CV 3 and 2. The difference in temperature between the state point 2 and 3. 1 to 2 is isentropic, is adiabatic, so we don't have heat transfer there. Our heat supply is only from state point 2 to 3, if you can recall the diagram just now. Okay, CV is considered as the specific heat capacity at constant volume. If let's say, for example, you are referring to A, it should be 0.718. Okay, QR is CV T4 minus T1, which is the heat rejected from state point 4 to state point 1. Okay, that happens in during the constant volume process as well. Okay, so if let's say, for example, you substitute the QS and the QR into the thermal efficiency formula, which we have defined just now, okay, we got this. And then when we strike off both the CV, which should be common, so what is left is T4, T1, T3, and T2 only in the equation. So what we are going to do is now we are going to simplify this so that the thermal efficiency here can be expressed in terms of volume ratio that we referred just now. Okay, so before that, okay, we refer back to what we have studied about heat engine, okay, earlier. So heat engine is an engine, okay, to which the supply of energy or the energy required or the gross energy is the heat energy that is supplied from the source, for example, from the solar, furnace, geothermal, steam, and etc. etc. Okay, so from there you have heat supply, and then it goes into our heat engine. Okay, so the heat engine will utilize the heat that is supplied and converted it to work or network output. But definitely not all the heat energy that is supplied to the heat engine can be converted to work. So the energy the heat energy which cannot be converted to work will have to be rejected to a lower temperature region. Okay, to a lower temperature region. Okay, so you have heat rejected, which is the energy which cannot be converted to useful work. We have to be rejected, otherwise your heat engine will be saturated, okay, full of unwanted energy, unavailable energy, so to the sink. Now, not advisable to use river, pond, or atmosphere anymore, or the surroundings. It is better for us to look into some substitution like cooling towers and etc. etc. Okay, to reduce river pollution or water pollution or air pollution. Okay, because nowadays it's very important for us to take into account of the global warming effect. Okay, so what we have here is the network out. So if you take heat supply minus the heat rejected here, you will have the network out. But the network out actually based on gas cycles is usually very low, okay, very low. So only a very small percentage of the heat energy can be converted to useful work. So based on the energy balance, you can say the energy input, that means going to the heat engine, must be equals to the energy output, that means away from the heat engine, which you have network out and heat rejected. So this heat supply will be equals to network out plus heat rejected. So that is why you get your network out is equals to heat supply minus heat rejected. Okay, that's here. Okay, so hope you are clear with it. Now, this podcast or this video is a little bit lengthy because, okay, I've compiled everything together. Hope you all don't mind. Okay, if you are don't have time to refer to the podcast as a whole, you can just break it up. Okay, watch at your leisure, yeah, or at your own leisure, or when you need any revise or revisions based on heat engine cycles. Okay, so we continue with this. Okay, we know that 1 to 2 and 3 to 4 is isentropic, isn't it? So we can make use of the temperature volume relationship only for isentropic. It is not applicable for isothermal, constant volume, or constant pressure. It's only for isentropic. So that this formula gives you the relationship between temperature and volume, which are with a power of gamma minus 1. This gamma here is called the adiabatic index. Usually for A is considered as 1.4. Okay, or you can use, okay, temperature, pressure, or pressure volume. But since this case is only the relationship between temperature and volume based on your TS diagram, so it's basically better for us to use the temperature volume relationship. So if you use temperature, pressure, or pressure volume, then you can refer back to my previous slides. Okay, so we got to know that V1 over V2. So we make use of the volume ratio now for this and for this as well. We know that V1 over V2 is equal to the volume ratio. V4 over V3 is also the volume ratio. Okay, so based on the thermal efficiency formula that we have derived just now, we can just simply write it down here, okay, afterward. Okay, so what we need to do is we need to change from this equation the T2 to be the subject and then V1 over V2 to be RV. So you can simplify it into this form. Then when you refer to this, okay, then you have T3 to be the subject. Then you have in terms T3 in terms of T4 and the volume ratio. This should be the volume ratio. Okay, so you have equation 1 and equation 2. Okay, so substitute your equation 1 into and 2 into the previous equation, this one. So you will have something like this. So you can strike off this and this. So what you have is something that is remaining here, that is the thermal efficiency formula, the most general formula. Okay, if let's say for example, if you want to find the thermal efficiency of Otto cycle, you can straight away, okay, use this formula if let's say the volume ratio is given or the volumes are found. Okay, so this slide here basically is a revision of what you have done in your previous, what we have done in the previous slide or the previous podcast or the previous video. So for isothermal, you can only be limited to use this, and then for isentropic, you can use this. This should be your gamma, or you can use as K, which is called the isentropic or the adiabatic index, and this is only for polytropic process. If let's say for example you want to find Cp or Cv or R or gamma, okay, or in terms of RO and M, you can use these formulas here to find out any of these if they are not given, if any of them are not given. Okay, so and then this is also a revisional notes based on constant volume process. Okay, from this you will be able to see during constant volume process what happens. Okay, so during constant volume process, we come back to PV diagram, and then we have a constant volume process here. This is just an example from the previous lesson actually. These are from the previous lesson, so you have to bear with me, okay, for a little time, okay, to go into a certain part of revision. Okay, so you have this. This is a constant volume process. So based on the non-flow energy equation, okay, we know that if volume is constant, this work here should be 0. Okay, so if the work is 0, then you will have heat is equals to the change of internal energy. So basically, you can use this to find out the heat rejected or the heat supply. It depending on whether it is 0.223 or 0.4 to 1. Okay, so basically the work done now here is 0, so you have only heat transfer, that is, for this case is heat rejected. Okay, you have in terms of the change of internal energy, and we know that U, that is internal energy, is equal to CVT. You can find U by having CV times the temperature, the absolute temperature, or the H for enthalpy to be equal to CPT. CP is a specific heat capacity constant pressure, and the T is the absolute temperature. Okay, so if you don't have a table or a gas table for a particular gas, you can always use this formula to find out the heat rejected or the heat supply by substituting your internal energy with CVT. Okay, so you have this. So remember, this is 0, this is 0, yeah? So you've got your heat rejected or heat supply to be equal to CV times multiplied by the changes in temperature. That is based on the non-flow energy equation. Okay, based on non-flow energy equation. Sorry, I'm using my mouse, yeah? Okay.